As Steve said, my name is Kyle Tetmeyer. I am the product security lead or chief program manager here for product security at Emerson Test and Measurement, or NI. I'm going to jump right in. Sorry, Hunter Artie and Steve have both led into the fact that we're going to talk about memory safe languages and particularly how it applies to LabVIEW. So I want to set the background a little bit. A number of years ago, I think this was around circa 2019, Microsoft basically did a study of their the vulnerabilities that were being reported, and they found that the root cause of vulnerabilities reported that Microsoft either fixed or assigned a CVE to, 70% of those were memory safety issues, right? So this is despite things like code reviews, training, static analysis, and others. Not to be outdone, Google also did a similar study of the Android operating system. And what they found was a couple of things. One is that most of Android's vulnerabilities occurred in two components, the media and the Bluetooth component. But of those, 90% of the vulnerabilities they found were related to memory issues as well. And then lastly, as another example, Google also has something called Project Zero. They hire a bunch of security researchers, and they're focused on 0 days. And so if you're not familiar with it, 0 day is essentially a security vulnerability that's unknown at time of exploit. So the patch has been available for exactly 0 days. And they performed a root cause analysis over a 10-year period from 2014 to 2024 of all the 0 days in the wild that they found, and 73% of those, 271 in total, were memory related as well. So when we talk about memory related issues, what are we talking about? And Hunter pointed this out in his part of the presentation, but we're talking about things like buffer overflows. We're talking about out of bounds reads and writes. We're talking about using uninitialized memory, use after free, double free, and those types of categories of issues. So the question was asked, rather than fix these one by one, what if we could just eliminate memory issues altogether? And that's where the use of memory safe languages comes in. So this slide is obviously a little focused on the US, but obviously the same concern and approach is being addressed around the world by other various regulatory and compliance organizations. But you can see there, right? The future of software should be memory safe, case for memory safe roadmaps, urgent need for memory safety. These are the headlines that are grabbing it. And I wanted to particularly point out this in the CISA and NSA guidance put out within the US. Reducing memory safe vulnerabilities requires understanding when MSLs are appropriate, knowing how to adopt them effectively, and recognizing where non-MSLs remain practical necessities. So we're going to dive into this a little bit more here as we go. So what makes a language memory safe? Well, as it turns out, there is not one particular standard or definition that defines that explicitly today. Every language has different features, different things it does. And so I'm not aware of it in my research to point to any specific standard. If you are aware, then feel free to drop it in chat and we can talk about it. But essentially what it comes down to in the common definitions that's usually used to define this is it's a list of bad things that can't occur within the language. So it's the things we just talked about: buffer overflows, null pointer dereferences, use after free, and use of uninitialized memory. Or it's something about what the language does. So the language uses garbage collection. It performs bounds checking. It does not allow for arbitrary pointer arithmetic. So this is the common definition that's out there that most languages, the standards that are used to define what a memory safe language is. So there are a few additional languages. Some are a little more niche, some are a little older, but these languages are the 6 most commonly considered memory safe languages. If you don't recognize the icons, we're talking about Python, Rust, C#, Go, Java, and Swift. These have been defined, mostly the NSA has put out a list. These are the languages that are on their list as default languages for being memory safe. But if you saw obviously the title of this presentation and the fact that we're here at NI, there's one particular language that's obviously missing from this list. So, or at least that's near and dear to our hearts. So is LabVIEW a memory safe language? So as part of that, I want to take you back to the definition that I proposed earlier. And again, a list of bad things that don't occur or things the language does. Right? And so if you look at it, LabVIEW performs memory management, except with a few exceptions, and we'll talk in a moment, and Hunter brought one up in his presentation, but obviously we don't allow, or we don't use pointers, there's no direct memory access, and it's also a strongly typed language, right? So what goes in the wire from one VI to the sub-VI to the next is going to be the same that comes out. So is LabVIEW a memory safe language? Well, again, because we're performing memory management and don't allow direct memory access, buffer overflows, null pointer dereferences, and all those things on the left-hand side of this do not occur. As part of memory management, we're performing bounds checking, and we're not allowing arbitrary pointer arithmetic. So by the definition that's put out there, yes, LabVIEW should be considered a memory safe language, at least on par with the other languages that we talked about earlier. So when I discuss this with people, I usually get, at this point in the presentation or at this point in the discussion, but what about some specific part of the language? In this case, if you're not a LabVIEW programmer or don't recognize that, but that's a call library node. LabVIEW supports the ability to call into other languages. Typically, it is referred to as foreign function interfaces. And if you're calling from a memory safe language into a language that's non-memory safe, potentially that can break the memory safe paradigm. That is correct. But every language that we talked about previously also supports these. So you can do the same thing in Python, in Java, in C#, and in Rust. You can call into other languages. So that in and of itself does not describe whether the language is memory safe. Now you need to understand what code you're calling and what memory safe issues it might have. But the existence of those is not something that makes the language memory safe or not. Not included in our definition, but some places will discuss resource exhaustion, right? Can I run it out of memory? And if you're a LabVIEW programmer and you drop down a while loop and you, with the shift register and append to an array, and you append to an array every time through the loop with no exit criteria, eventually you're going to create, your array is going to grow unbounded. And you might see that message there that says LabVIEW memory is full. Again, that specifically is not something that is commonly included within the definition of a memory safe language. It is certainly a concern. It is something that users need to be aware of and need to handle. But even garbage collected languages like Java can run out of memory and other resources. So the existence of the ability to run out to exhaust memory or other resources does not clearly define whether a language is memory safe or not. And then I'm going to group this last category, and we talked a little bit about the Memory Manager API and LabVIEW and others. But what about any other unsafe functionality as well? And there are cases where that is true. But I certainly want to point out, Rust, C# and other languages support the unsafe keyword. They support this escape hatch to go into areas where you may need to, for one reason or another, use unsafe functionality. We suggest that obviously to maintain memory safety, that should be minimal. You should attempt not to use those when if possible. But as NI, we need to document which of those functions and functionality breaks memory safety. As users, you need to be aware of which of those language components you're using and whether you need to be concerned about memory safety or not in those. But again, in and of itself, the existence of specific unsafe functionality is not something that breaks whether something is memory safe or not. So the other aspect that's brought up and questions are asked, hey, but parts of LabVIEW and NI drivers, are not written in memory safe languages. And yes, that's true. I mean, legacy code is the thing. It's not something that we can easily just eliminate, rewrite everything and snap our fingers and 40 years of development is changed into a memory safe language, right? We need to do that appropriately. And I'll go back to the guidance that was presented out there by CISA and the NSA, at least in the US, use MSLs where appropriate, but recognizing where the use of memory safe languages remain practical necessities, right? So we need to balance sometimes performance, complexity, as well as prove it in use. I mean, there are drivers, there's code you call that may not call in any, perform any memory actions, right? And so the fact that it's written in a language that is non-memory safe itself does not mean that it cannot be memory safe. And so some of these trade-offs, right? We need to continue to balance that and over time be moving to it and into this memory safe world. So I'm gonna close too. We talked about Microsoft, but actually the Linux kernel also now allows Rust as a programming language within the kernel, but most of this is written on non-memory safe languages. And so, but just like we talked about what Microsoft was doing, they have started to rewrite some of the kernel level components in these memory safe languages. And over time, they're adding additional ones and they're supporting it. But if you notice, the top level applications and drivers don't necessarily change, right? It's agnostic to the user below that. And very similar, in LabVIEW, when you're writing your LabVIEW application and you're calling into runtime engine or you're calling other NI components or drivers, over time, as we also improve and rewrite or deliver new drivers or new components in memory safe languages, you're able to take advantage of that and gain that memory safety without any changes to your LabVIEW application. So that was a very quick, in interest of time to get through in memory safe and introduction. If there's any questions, I know there was a question in the chat. I don't know if it's been answered yet. There is a paper published up on ni.com. If the link is not in there, I'll drop it in a moment.
There's one question, Kyle, about variants. In LabVIEW, one of the data types is variant. Does that break the strongly typed assertion?
Again, we can go into detail about what you're doing within that variant, right? I mean, it may break that paradigm. You have to understand where those things are occurring.